So let's find the area between the following curves. F of x equal to 3x cubed minus x squared minus 10x, and g of x equal to negative x squared plus 2x. So we could graph these. We don't really have to graph them though. And so what I want to point out is most of the time when you're finding the area between just two curves, you really don't have to graph them. If you have like 3 or more, then you typically kind of really need to see what region you are bounding with those multiple curves. But for 2 graphs, we just have to find where they intersect. So let's set them equal to each other to find the points of intersection. So let's see. So 3x cubed minus x squared minus 10x equal to negative x squared plus 2x. I'm going to bring everything over to one side. I'm going to pick the left side. Notably, it looks like the x squareds actually cancel out. So I'm going to get 3x cubed minus 10x minus 2x is minus 12x equal to 0. If I factor out a 3x, I'm left with an x squared minus 4 equal to 0. And then I can factor that further and get an x minus 2 times an x plus 2 equal to 0. So here I'm actually getting 3 distinct points of intersection. I'm getting x equal to 0, 2, and negative 2, which means we have to actually write this as 2 integrals because there's 2 different intervals where one function might be on top and one function might be on the bottom. So what we're going to do is we're going to say this is going to be the area between the 2 curves is going to equal the integral from negative 2 to 0 of whichever function's on top minus whichever function's on the bottom, plus the integral from 0 to 2 of whichever function's on top minus whatever function on the bottom. And the thing that's interesting about this problem is, or any problem where you have more than 2 points of intersection, is the function that's on top might change. They might cross each other in that way. So the way I always like to tell which one's on top is pick a point between these 2 endpoints. So I'm going to pick x equal to negative 1 and plug it in. So f of negative 1 is, let's see if I plug it back into my function, it's 3 times negative 1 minus 1 minus 10 times negative 1 is plus 10. And that's negative 4 plus 10, which is 6. And g of negative 1 is going to be, let's say I plug in negative 1 to g, it's going to be negative 1 minus 2, which is negative 3. So for this function, or I should say, for this interval from negative 2 to 0, the function that's on top is f of x. On the other hand, for this interval here from 0 to 2, if we set x equal to positive 1, then if I plug it in for there, f of 1 is going to equal 3 minus 1 minus 10, which is negative 8. And g of 1 is going to equal negative 1 plus 2, which is positive 1. So here, g is the bigger function. So if I'm setting up this integral, the area is going to equal the integral from negative 2 to 0 of the top function minus the bottom function. So it's going to be f of x minus g of x. So 3x cubed minus x squared minus 10x minus negative x squared plus 2x dx plus the integral from 0 to 2 of g of x minus f of x. So negative x squared plus 2x minus 3x cubed minus x squared minus 10x dx. And I feel like I'm in that little region there where you can't quite see. There we go. So that's how we would set this up. And then if we actually want to compute it, we would do the following. So I'm going to first do one thing to make this a little bit nicer. I'm going to simplify. And so here's something worth noticing. Oops. So right, this is your f minus g. This is your g minus f. So when I simplify this, I'm going to get the integral from negative 2 to 0. Well, we already did the subtraction before. And 3x cubed minus x squared minus 10x minus negative x squared plus 2x, that's going to give me a 3x cubed minus x squared minus x squared cancels. And then the minus 10x minus 2x is minus 12x. And here's the nice thing to know. When you subtract things in the opposite order, they're the negative of each other. So g minus f is just going to be negative 3x cubed plus 12x. It's an easy way of doing that. And then we do the not so fun part. Oh, question. Yeah, in fact, yes, and we have an example, yes. And I'll show you an example of that in a minute. So, sorry, so then calculating this, we're going to get 3x to the fourth over 4 minus 12x squared over 2 from negative 2 to 0 plus negative 3x to the fourth over 4 plus 6x squared from 0 to 2. And then plugging in, so plugging in 0 first, we get 0 minus 0 minus plugging in negative 2, we're going to get 3 times negative 2 to the fourth is 16 over 4 minus 6 times negative 2 squared is 6 times 4, which is 24. Plus, then we plug in 2 here, we're going to get negative 3 times 16 over 4 plus 6 times 2 squared minus 0 minus 0 plus 0. Sorry. There is some symmetry here, which is why the numbers are coming out to be similar. Why is it 6 and not 12x squared? Oh, it is, well, it's 12x squared over 2, right? So when we anti-differentiate x, we get x squared over 2. So 12x squared over 2 is going to reduce to just 6x squared. That's what's happening there. And then we're going to get, let's see. So 16 over 4 is 4. So I'm going to get negative 3 times 4 minus 24 plus, same thing here, 16 over 4 is just 4. And negative 3 times 4 is a negative 12 plus 24. So we're going to get negative 12 plus 12, which is 24. Couple things to observe here. So we didn't need to graph this one, but just so you can see kind of what's happening here is your function f kind of looks like this. And your function g kind of, let's see, sure, kind of looks like this. So from negative 2, so I didn't graph it perfectly, right? Kind of from negative 2 to 0 is where f would be on top. So right here we have f on top and g on the bottom, and you get that area. And then in the second part, from here to here, you have g on top and f on the bottom. So that's why this is working out this way. Now I know I didn't drop perfectly, but that's kind of the idea here is why you need to check. But let's look at another example that is a little bit the same, but a little bit different. So yeah, let's keep things in order here. Let's say we wanted to find the area between these two functions. F of x equal to, sorry, I need to think for just one second because I don't actually. Okay. Sorry, 1 second. I just have to think about how this looks. I think I want 2 to be intercept. So sorry, I know this function almost. I just let's see, going down like that. I want those 2 points. So I want 16. Yeah, I think I want a 4x squared minus x to the fourth. Yeah, that'll work out all right. And g of x can be x squared minus 4. Nope, not x squared minus 4, just x squared. Yeah, that'll be, yeah, sure. Sure, it's going to be not lovely, but it'll be fine. So, oh, sure. So back to the previous example for just 1 second. So I'm assuming you're asking about plugging in the numbers. So the reason why, so for here, to figure out which one was on the top or the bottom, So let me actually redraw this picture just a little bit better because this is not quite perfect. So it's actually more like this, where F looks kind of like this, and G looks kind of like, sure, let's see what it looks like -2. G looks kind of like this. Not perfect, but it's fine. So I didn't draw it, and I didn't need to. But what I saw was that if this is my function f and this is my function g, I know they intersect when x is -2, when x is 0, and when x is +2. And so to kind of be able to tell which function is bigger, well, between -2 and 0, since they only cross there and there, between -2 and 0, one of them always has to be on top, one of them always has to be on the bottom. So I pick a number between -2 and 0. Oh, I'm going to pick -1. And when I pick x equal to -1, I got f of -1 equal to +6 and g of -1 equal to -3. So that told me, oh, between -2 and 0, the g function always has to be on the bottom and the f function always has to be on the top. And then I did the same thing between 0 and 2. I said, oh, okay, I'm going to pick x equal to +1. I'm going to plug it in, and f of +1 is going to be -8. Ooh, but yeah, sure. And g of +1 ended up being +1. And now again, I know my pictures aren't perfect, but essentially, right, here's your g of 1 equal to 1, and here's your f of 1 equal to -8. So since f is the smaller function at this one point between 0 and 2, it has to be the smaller function for every point between 0 and 2, because the only places where they cross are at 0 and 2 there. So that's what's happening there. That's why I picked those points. Does that clarify things? Let me go with yes. So let's look cool. So let's look at this next one, which I feel like the numbers I made up are going to be terrible. That's okay. So again, I want to find the area between these two functions. I really don't want to have to graph them. So we're just going to set 4x² minus x to the 4th equal to x². And now I personally prefer to bring everything to the side that makes the highest power of x positive. So I would probably bring everything to the right. And so I'm going to have 0 equal to positive x to the 4th minus 4x² plus x². Or 0 equal to x to the 4th minus 3x². Yeah, my numbers aren't going to be that nice. It's okay. So factoring, So factoring, I get 0 equal to x² times x² minus 3. And just like the previous problem, I'm going to have 3 points of intersection. I'm going to get x equal to 0 and x equal to plus or minus the square root of 3. I know it's not lovely, but it's actually not as terrible as it looks. Maybe it's a little terrible. It's fine. So doing this, we see, okay, I have 3 points of intersection. Now, I'm not going to draw right with my integrals yet because I'm just going to test. So on the interval from -√3 to 0, one of the functions has to be bigger. So pick a number between -√3 and 0. The only nice number between -√3 and 0 is -1. So I'm going to let x equal -1. F of -1 is 4 times -1 squared minus -1 to the 4th, which is just 1. That's going to be 3. G of -1 is just 1. So f is bigger on this whole entire interval. And then we're going to do the same thing in this interval here, x equal to 1. But f of 1 is also 4 minus 1, which is 3. And g of 1 is also 1. And again, we get f bigger than g here. So in this particular instance, f is always on top. So we don't actually need to use two integrals. We can say, oh, the area is just going to equal the integral from -√3 to +√3 of f minus g, because f is the bigger function. Now this actually also allows us to do something else, which is going to make it a little bit nicer. So f is 4x² minus x to the 4th minus g, which is x² dx. I would point out that this function is an even function, right? If you replace x with negative x, it's the same. Or you can just see, since it's a polynomial and all the powers are even, it is an even function. Which means it has that symmetry about the y-axis, which means we could rewrite this as twice the integral from 0 to 3, the root 3 of, I'm going to simplify this a little bit, 4x squared minus x squared, 3x squared minus x to the 4th. It just makes it a little bit nicer when you actually have to evaluate the integral. So then we would do the antiderivative. It's going to be x cubed minus x to the 5th over 5 from 0 to root 3. And then we would just plug it in and we get 2 times the square root of 3 cubed minus the square root of 3 to the 5th over 5 minus 2 times 0 minus 0, which I don't think we need to write. Sorry, it's off the page, I know. Should go horizontal. The vertical is just a little too long, like it doesn't quite catch all of it. And I would probably just leave it like this. If you really, really want, you could rewrite this as 2 times 3 to the 3 halves minus 3 to the 5 halves over 5. There is more simplifying that could be done, but it's not really worthwhile. It's not going to show you anything new that's particularly interesting. In case you're curious, the reason this is happening for this one is that graphically, g of x looks like this, right? It's your good old square root function. And f of x looks, let's see, it's got intersects at 2. Yeah, so f of x looks kind of like this. And so we're getting the area between f of x and g of x. And look, f of x is always on top. But again, you don't actually have to be able to graph them to see which one's on top and which one's on the bottom. So I highly, highly recommend finding where they intersect and then picking a point between the points of intersection to see which one's on top. Okay. Sometimes we want to, well, sometimes we need to do something different. Let's say I want to find the area between x equal to 4 minus y squared and y equal to x divided by 3. Okay, so again, you don't have to graph these, but I think we should here because, well, one, we're writing x as a function of y, not y as a function of x. So I'm going to draw, so x equal to y squared is a rightward opening parabola. So x equal to negative y squared is a leftward opening parabola. Sorry, I'm going my left, not your left. Is a leftward opening parabola. And then we're going to shift it forward in the positive x direction. So this is going to actually, what I would really actually do here is plot a point. If y equals 0, x is going to be 4. And if y equals 1 or negative 1, x is going to be 3. And if y equals 2 or negative 2, x is going to be 0. So now you can kind of start to see, oh yeah, this is a leftward opening parabola. And then y equals x over 3 is just a straight line that goes to the origin. It has the point 0, 0 and the point 3, 1, and looks kind of like that. And these probably intersect somewhere over here. Yeah, sure. So I'm trying to find this region here. And while you certainly could use vertical cross sections or vertical strips to do this, it's not really ideal, especially because when you're doing vertical strips, we're supposed to do the top function minus the bottom function. Well, if I did vertical strips, that would mean 1, I'd have to use 2 integrals because right here, my top function changes from y equals x over 3 to this other function here. And second of all, for this part here, your top function and your bottom function are actually the same function, which we can deal with, but becomes kind of challenging. So in other words, what we should actually do is think of using horizontal cross sections, where instead of doing the top function minus the bottom function, we're going to actually do the right function minus the left function. So the area here is going to equal the integral of the right function minus the left function, dy. And our limits of integration are going to be y equal to the bottom value all the way up to y equal to the top value. So it's just like before, except before you do top minus bottom function and you go x from x equal to the leftmost value to x equal to the rightmost value. Now we're just kind of totally interchanging things. So a couple things, let's find where they intersect. So intersection, it might be helpful if I actually rewrite y equal to x over 3 as 3 times y equal to x. So then I can set this equal to that and get 3y equal to 4 minus y squared, or bringing everything to the left, y squared plus 3y minus 4 equal to 0. And then I'm getting y times, y plus 4 times y minus 1 equal to 0. So looks like my points of intersection are y equal to -4 and y equal to +1. Which jives with our picture, right? If we already saw that if y equals 1, x is 3, oh yeah, we have the point 3, 1 right there. And we can see over here, if y equals -4, we're going to get x equal to 4 minus -4 squared, which is 4 minus 16, which is -12. And that seems reasonable, at least from what our picture looks like. So then we're going to do the integral of the right minus left. Now, how do I know which one's the rightmost function? Well, I drew it, so I'm pretty sure it's going to be 4 minus y squared minus 3y, or this is the right, and this is the left. But if we didn't draw it, we could apply the same logic as the previous problems. We say, okay, well, when you're doing things in terms of like x, the higher function has the higher y value and the lower function has the lower y value. When you're doing things in terms of y, the rightmost function has the bigger x value and the leftmost function has the lesser x value. So to figure out which function's the right one or the bigger one, we need to figure out which one has the bigger value when you plug in values of y. So I know they intersect at y equals -4 and y equals 1. So here they intersect and they have the same x value. Sorry, here they intersect and they have the same x value. They both have an x value of 3. Here they intersect and they both have the same x value of -12. So we're going to pick a y value between -4 and 1 to figure out which one has the bigger x value. So we're going to set or pick, I'm going to pick y equal to 0. If you can pick 0, it's usually a good choice, right? If 0 is between your 2 points of intersection. So then we can see that for the first function, x equal to 4 minus y squared, we're going to get x equal to 4 minus 0. And for the second function, x equal to 3y, we're going to get x equal to 3 times 0, which is 0. And that's the bigger value. So this is the rightmost function, which is what we already saw. So again, just want to point out, you really don't have to draw the functions here. It's a good idea too. It's nice, but if that's hard for you, a lot of the time you can skip it. So then we also need our limits of integration. That's just going to be from the bottom value of y to the top value of y. So when you're doing things horizontally, your function is a function of y. Your d whatever is a dy. I should say that's your differential. Your differential is dy. And your limits of integration are from a low value of y equals -4 to a high value of y equals 1. So everything's in terms of y instead of being in terms of x. And then the rest is not too terrible. We're going to anti-differentiate. We're going to get 4y minus y cubed over 3 minus 3y squared over 2. And then we would plug in -4, 1. And then we could plug those in. So this is kind of just doing it. 4 times 1 is 4. 1 cubed is 1. 1 squared is also 1, so 3 halves. Minus, and you plug in -4 and you get -16 minus -64 over 3. Oops, I didn't mean to close that off just yet. Minus 3 times -4 squared is 3 times 16, which is 48. And then we could do more simplifying, but again, sorry, I'm off the page. You guys should tell me if you can't see it. That would equal some number, but that's not really important for me. I assume no one is talking about the midpoint rule or the trapezoid rule yet. Like if those things sound foreign to you, that's good in that I have looked at your homework assignments and I haven't seen any of those types of problems. So I imagine, right, is anyone on Zoom, midpoint rule, trapezoid rule sound at all familiar? I hope the answer is no, in that you're not talking about it in class yet. Also, here's the attendance form again in case you need it. Okay, that's what I thought. So let's move on and start talking about volumes. If you're in Cron's class, don't worry, you're going to get to volumes. It's definitely something she's going to cover. I know you haven't talked about it yet, but we're going to get there. And it's definitely important to talk about volume in the same context that we talk about area because they're very related to each other. And I really think I should go, keep falling off the bottom of the page. Let's just go horizontal like I should have from the beginning here. Okay. So just do this tiny bit here. Sorry, 1 second. Just. Okay. So let's talk about what we're doing here. This is section 5.7. Volume. Typically volume, I should say volumes of revolution. Revolution. Meaning we're going to take a region and we're going to revolve it around an axis to get some three-dimensional shape, and then we're going to find its volume. So let's say we're going to do this. We're going to find the volume of the solid formed when the region, which we'll call A, in quadrant 1, bounded, there's a lot of words for these problems. Like there's a lot of like, okay, all the things. Bounded by y equals x cubed, y equals 0, and x equals 2 is revolved about the x-axis. Okay, it's a lot of writing, but let's see what you guys. So we can totally draw a picture here. So let's be careful, and we should draw pictures here. So we're in quadrant 1, meaning x and y are both positive. We're looking at the function y equals x cubed, y equals 0, and x equals 2. Okay, that's not too terrible to draw. Y equals x cubed has this kind of shape. X equals 2 has this vertical line shape. Right, shape is kind of an overstatement there. And y equals 0 is the x-axis. So here's our region, our area that we're going to revolve around the x-axis. And so what I also don't necessarily recommend, but am going to, is I'm going to draw the revolved shape. So we're going to take the shape. What we're going to do is we're going to revolve it around the x-axis. Now, if I'm drawing a shape that's revolved around an axis, what I typically do is I draw that curve and then I reflect it across the axis I'm revolving around. So I'm just going to reflect that down. I'm going to try and mirror it as best as I can. It doesn't always work out perfectly, but that looks pretty good. And then I'm going to try and make it look 3D. So I'm thinking of this as revolving down like that, coming back like that. That's like behind the axis there. And then, right, it's kind of got this kind of deal. So there's our shape. Now, the question is, how do we find the volume of that? Well, here's what we're going to do. We're going to take a vertical strip in our region. And when I revolve that strip around the x-axis, what do I get? Well, essentially I'm taking a little rectangle and I'm sweeping out a full rotation and I'm going to get a disc. So this little rectangle has some small thickness to it and it's going to give me this disc shape when I rotate it around the x-axis. And we can find the volume of that disk. So I should write these words. So when we rotate a vertical rectangle around the x-axis, we get a thin circular disk. So now what we're going to do is, instead of taking the idea of adding up a bunch of rectangles to find area, we're going to add up a bunch of disks to find volume. I should say, we're going to add up a bunch of volumes of disks to find total volume. So what is the volume of this disk? Well, the volume of this disk, very, very generally, it's a circle with some thickness. So it's going to be the area times the thickness, which is going to be, well, the area of a circle is kind of always the same. It's pi r squared. And the thickness is a small change in x, right? It's this little bit here, which is our dx. That's your small change in x. So now it's important to recognize that depending on where we are in this region, the radius is going to change, right? At this point here, that's my radius. But if I drew like this little one instead, right, my disk would be much smaller. So the radius is variable. The radius in this particular problem is just the height of the function. It's how far above the x-axis we are. So the radius here is actually x cubed. I feel like someone's just like turning on the water and then, okay. So the radius here is x cubed. And generally, the radius is how far away we are from the axis of rotation. So then we're going to say the volume of our disk is going to equal pi times the radius squared times dx. So that's the volume of this one disk. But now we want to find the total volume. That is, we want to quote unquote add up all the disks. Well, the way we quote unquote add up all the things when there's like an infinite number of them that are really, really narrow is we integrate, right? Our adding up all the things is the integral from here to here of all of your disks. So our disks go as far left as, in fact, let me draw in some disks now, right? Here's a disk. Here's a disk. There's some good pictures in the book about like showing a bunch of like slices of things that look like you basically took a thing and then had a bunch of disks that were kind of added up together. And then they show you like pictures with like narrower disks, so it looks like a better approximation. The book is expensive and is good for like having the homework problems in it and maybe reading some things, but the book has really nice pictures. So most of us paid for this book at some point. Use it for the pictures. The pictures are good. Go look at the pictures. I highly recommend it. But here we're adding up all the disks, and the disks go as far left as 0 and as far right as this was x equal to 2. All right, this is x equal to 2. So that's how we're going to find the volume here. And it's going to equal the integral from 0 to 2. We can bring out that pi of x to the 6 dx, and then we're going to get pi times x to the 7th over 7 from 0 to 2. Oh, I know. I'm stupid. Sorry. This thing's in the way. This thing is in the way. It doesn't want to be out of the way. Okay, fine. I'm not stupid. I'm just annoyed. That's what I am. Anyway, plugging in the 2, we're going to get pi times 2 to the 7th over 7 minus 0 to the 7th over 7. So we're going to get 2 to the 7th, which is 128. Is it 128? Yes, 128. Pi over 7. Cool. Kind of neat. So now we're going to do it again, but we're going to talk about rotating around the y-axis. So most of the time, these are the two axes we're going to rotate around, either the x-axis or the y-axis. Now, the y-axis offers some extra kind of things to think about, which is that if we rotate around the y-axis, well, let's draw the picture again. So here is my, let's see, how do I want to draw it this way. And this piece of paper looks less than excellent. Let's do this instead. So let's go around the y-axis. And here's my region once again. Something like this. And although I know this function does go on, I don't really want to draw more of it than I really need. So here's again, x equal to 2. Here's y equal to x cubed. I don't really need to write y equal to 0 there. But we're looking at this region. But now we're going to go around the y-axis. So again, to draw around the y-axis, I'm going to reflect this thing across the axis and then draw. So what I would recommend if you're trying to draw these things is if you're reflecting this part over this way, draw the thing that's kind of the outermost function, but maybe draw the inner thing dashed because it's kind of going to get covered up. So I'm going to draw this here. I'm going to reflect that over here. So it's going to be about right there. And then I'm going to draw this part here dashed. So it's kind of like this. It's kind of like this. Because what's happening is I'm taking this region and I'm rotating around the y-axis. What I'm getting is some sort of like, it's kind of like a cylinder where I've cut out like a bowl shape from it. So that kind of let me finish drawing it. Right, so I've got this, right? I don't really have a good look. I'm trying to think of like a physical thing that would mimic this, but I can't really think of one. Like you've got some cylinder. Okay, here's maybe a good example. You've got a container of ice cream and you have scooped it out in such a way that you've kind of left this bowl shape in it. We're trying to calculate the volume of ice cream that's left, right? Because so here's the ice cream that's left. Here's the ice cream I've scooped out. That's a not terrible interpretation of what's going on here. All right. So what we're going to do now is the same sort of thing. Instead of taking a vertical strip, though, we're going to take a horizontal strip and rotate it around the y-axis. Now, the difference between this problem and the previous problem is, in the previous problem, well, there's a couple differences. Obviously, we're doing a different axis. But another difference here is that in the previous problem, when I rotated this strip around, I got a disk because the strip was right next to the axis of rotation. Whereas in this other problem, when I rotate this strip around, I'm not actually going to get a disk. I'm going to get a disk that's missing the inner part. I'm going to get what we typically call a washer. So I'm going to rotate this thing around here, and I'm going to get this washer shape. Oh, it's good. Okay, that could be better. With a little bit of thickness to it. And so just like before, what we're going to do is we're going to find the volume of this particular slice, and then we're going to add up all the slices. In the previous problem, we were adding up all the slices that were disks. Here, we're going to add up all the slices that are washers. So the volume of my slice, or the volume of my washer here. So it's very, very similar to the disk in that you've got circles with thickness, except now it's a big circle minus a little circle and then times the thickness. So the volume of the washer is the big circle area minus the little circle area, circle, I can spell circle, times the thickness. In other words, it's pi times whatever the larger radius is minus pi times whatever the smaller radius is, all times. In this case, the thickness is, I've only got one person to ask. Devin, what's the thickness? Is it dx or is it dy? Right, exactly, because it's a small change of y. So if you're using vertical strips, it's always a dx. If you're using horizontal strips, it's always a dy. Because a vertical strip has a small change in x, a horizontal strip has a small change in y. Okay. And so then we have to identify what our outer function or inner function is. So since we're using dy, we're thinking, oh, our functions have to be functions of y, meaning we need x equal to some function of y. So our outer radius, the function that's further from the axis of rotation, that's going to be x equal to 2. Not very exciting. It is a function of y, it's just a constant function. Our inner radius, the function that's closer to the axis of rotation, is going to be this function here, y equal to x cubed, but we have to solve for x as a function of y. So it's actually going to be x equal to the cube root of y. And again, just to really point out, this here is my inner radius, and this is my outer radius. So then we can write that the volume of our washer is going to equal pi times 2 squared minus pi times the cube root of y squared, all times dy. And then the total volume, again, the total volume, we are just adding up all the volumes of the washers. So that's going to be the integral of this thing. And I'm going to simplify a little bit. There's two easy simplifications we can do. We can factor out the pi, right? The pi definitely comes out in front of the integral. And then we can simplify our expression. 2 squared is 4. Cube root of y squared is y to the 1/3 squared, which is y to the 2/3. dy. And then our washers go as low as y equals 0 and as high as whatever this point is here. If x is 2, the y value is 2 cubed, which is 8. So our limits of integration are from 2 to 8. Sorry, from 0 to 8. The rest is typically not too terrible. So we're going to get pi times, I will warn you to be careful or to pay attention if I make this mistake. It's often very easy to accidentally drop this pi. Like for some reason, it just wants to disappear all the time. People like pi, what can I say? So make sure you keep that pi there. It does often, I'm 100% sure at some point I will forget to write it in one of the things and you should be like, hey, James, you forgot the pi. So integrating this, we get 4y minus y to the 5/3 divided by 5/3 is like multiplying by 3/5 from 0 to 8. And then we plug in and we get pi times 4 times 8 is 32 minus 3/5 times 8 to the 5/3 power. Seems terrible, but let's think about this. 8 to the 5/3 is the cube root of 8, which is 2, raised to the 5th power. And 2 times 2 times 2 times 2 times 2 is 32. And I will say we're seeing this, we've seen this kind of trick before, where you have two things that look kind of terrible to put together, but they both have the common factor or common number in them. So we should totally factor out the 32, and then we're left with a 1 minus 3/5. And that's much easier to deal with fraction subtraction. So 32 pi times, that's going to be 1 minus 3/5 is 2/5. So I'm ending up with 64 pi over 5. Cool. Let me look at one thing here before I get to, I just want to see, I wonder if your volume problems have any of this stuff yet. Okay, there's like a couple of them, so we'll wait on that. Let's do a few more practice problems. Yeah. So, got some examples from this, sure. Now, I should point out, now I know you don't have any homework problems like this, but a lot of the times these homework problems say set up the integral, but don't actually calculate the integral. And that's because a lot of the point of doing it is being able to set it up. And then we start to kind of make the assumption that like, yeah, you can calculate that, right? It's not like a terrible integral. It's not like some weird U sub or whatever. So a lot of times the problems are going to be just to set it up, not to actually calculate it. Let's look at the following. So let's say I want to find the volume of the solid obtained by revolving the region bounded by, sure. Yeah, that's a good one. Y equal to, sorry, brain. Yeah, why not? Y equal to the square root of x and y equal to 1/3 x about the x-axis. Maybe we'll find it, maybe we'll just set it up. We're at least for sure going to set it up. So you don't have to draw the, I'm trying to talk, who am I talking to? You don't have to draw the region. Let's see if we can do this without drawing the region, and then we'll kind of come back to it. So I want to find the points of intersection. So these intersect when, well, let's let them equal to each other. Square root of x equals 1/3 x. Before I square both sides, I totally could square both sides right now, but I'd rather not deal with fractions. So I'm going to multiply both sides by 3 and then square both sides. So that I get 9x equal to x squared. And now I really shouldn't divide by x. So I divide by x, you'll just get x equal to 9, and you'll miss x equal to 0. What I should do is bring everything to one side and then factor out an x. And then get x equal to 0 and x equal to 9. So those are my limits of integration. And that's typical, right? The points of intersection are often the limits of integration. So now, no, I really like, as much as I would like to encourage you to be able to do things without drawing the pictures, drawing the graphs is an important skill, and it's kind of necessary. Like, it's hard to tell for this one whether you need the disk or the washer method. So I will point out the disk and the washer method are really kind of the same. They just have the disk, the washer method just has kind of like an extra piece. So I really want to draw them. So y equals root x looks like this. Y equals 1/3 x. Well, we know they intersect at 0 and 9, so like maybe they intersect right here. Wow, look at that. I actually got to go to the point I picked. So here's how you know something is the washer method versus the disk method. It's the washer method if there's space between your region and the axis of rotation. Another way of saying this, so actually I should write this down because it's kind of important. Washer method, how do we know? One way of knowing when you draw the picture is there is space between the region that you're revolving and the axis of rotation. That's why in the previous two problems, right, for the first problem when we revolved around the x-axis, we didn't need to use the washer method because there wasn't any space between the axis of rotation and the region. Whereas when we revolved it around the y-axis, we did need to use the washer method because there was space between the axis of rotation and the region. Another way of saying this is that we use the washer method when the axis of rotation is not one of the boundaries of our region. That's the way I've come to think of it most conveniently, especially if I didn't want to draw it, right? If I didn't want to draw this thing, I could be like, well, my axis of rotation is the x-axis. And what's the equation for the x-axis? Yeah. Is y equals 0 one of my boundaries? No, it's not, right? Our boundaries are y equals root x and y equals 1/3 x. So knowing that is not one of my boundaries, to be like, okay, I'm almost definitely going to have to use the washer method. That's another way to think about it. Okay. So then we're trying to, and I do like to draw this picture. We're taking our little strip here, which is not flush with the x-axis, is another way I like to say it, right? It's not butting up against it. And then we're rotating that. So it's gonna, you know, there's our little, there's our washer. And the volume of our washer, once again, is pi times, I usually like to factor out the pi right from the beginning. So it's pi times the big radius squared minus the little radius squared, all times dx in this case. One common mistake that I see with problems like this is people like to subtract the functions and then square it. That's not correct. We have to square each thing first and then subtract them. So here, the volume of my washer is going to equal pi times, okay, the outermost function, this is where drawing it really is helpful. The outer function is clearly the square root of x. The inner function is clearly 1/3 x. So then the total volume we're going to calculate by doing the integral from as far left as 0 to as far right as 9 pi times the square root of x squared minus 1/3 x squared dx. And yeah, we might as well calculate it. It's pi times the interval from 0 to 9. Square root of x squared is nice. 1/3 x squared is 1/9 x squared. Not terrible. And then if we anti-differentiate, we're going to get x squared over 2 minus x cubed over 9 times 3 is 27 from 0 to 9. Now check this out. The trick that often happens when you do some interesting definite intervals is going to happen again. I'm going to get pi times 9 squared, which is 81 over 2, minus 9 cubed, which I don't know what 9 cubed is, but look, if I write 9 cubed over 27, one of those 9s is going to cancel, right? 27 definitely has a factor of 9, and 9 cubed definitely has a factor of 9. So look what I'm left with. I'm left with pi times 9 times 81 over 2 minus 9 squared, which is 81 over 3. And I can factor out an 81 and get 1/2 minus 1/3 left in the parentheses. And 1/2 minus 1/3 is 3/6 minus 2/6, which is 1/6. So we're getting 81 pi over 6, which reduces to 27 pi over 2. Or 13.5 pi if you like decimals. Let's see. Okay. Let's do another one. Yeah, sorry, where'd you go? Okay, so let's do that. Interesting. Sure, that's a good point. Yeah, I want to make it not too terrible. Let's do that. So let's say I want to set up but not find. So we're going to set up integral to find the volume of the solid formed when revolving the region bounded by y equal to, let's go big, 100 minus x squared and y equal to 0 about, well, we're going to pick a few different axes here, but we're going to start with the good old x-axis. So again, I think drawing the picture is a good idea. This is a picture that should come pretty naturally, meaning y equals 100 minus x squared is a parabola that upwards downwards. It's been shifted up 100. It's going to look like that. We even have a pretty good idea of what the intercept should be. That's going to be 0, 100. That's going to be 10, 0. That's going to be negative 10, 0. So we're taking this region and revolving it around the x-axis. We're just going to get it kind of flipped over. And we're going to get, are we going to get discs or washers? Good question. What do you guys think on Zoom? Discs or washers? Like, is there anybody on Zoom? I'm pretty sure there's people on Zoom. Like, I can't. Yeah, there's like 2 people. So for the 2 people on Zoom, what do you all think? Am I using discs here or am I using washers? Are you there? Are you? What was that? Yeah, we're definitely using discs because all the things, right? The region has the x-axis as one of its boundaries, or you can also say that the region, there's no space between the region and the x-axis, or a third way I like to phrase it is the region is flush with the axis of rotation. So we're definitely using the disk method. And that's just that the volume of our disk is pi times the radius squared times dx in this case, because we're definitely using dx. One way to think about if you're using dx or dy is your strip that you're thinking about drawing, that I really think you should draw this strip every time. Your strip should always be perpendicular to your axis of rotation. So my axis of rotation is this axis here. It's a horizontal line. My strip is perpendicular and it's got a small change in x. Or a vertical strip always corresponds to a dx. Horizontal strip always corresponds to a dy. So our total volume is going to be the integral from negative 10 to positive 10 of pi times my radius, which is 100 minus x squared, dx. And that's it. That's all we have to do. So now let's ask a different question. A related question. What if instead, and we're gonna ask like we're gonna do like 3 or 4 variations. What if we wanted to go around, say the line y equal to negative 2? So again, here's our region, but now here's my axis of rotation. So now let me ask you, am I going to use the disk or the washer method? Right, I have to use the washer method now because my axis of rotation is not flush with my region, or because there's space between my region and my axis of rotation. I'm still going to use the same strip as before. I still have the same vertical strip. But the difference is before, right, let's go back to before. Before, when I revolved this strip around the axis of rotation, I was just getting a nice disk. Wow, this pen is starting to wear out. Right, so I got a disk before. But now, when I revolve this new region, this strip around this new axis of rotation, well, when I revolve it, I like to have space when I do this. Right, I'm revolving around this axis. So this point's kind of revolving down there. This point's revolving down there. So I know my picture's not perfect, but right, there's my new washer. So my outer radius is that. So in fact, my radius isn't the same as before. My outer radius is going to be 100 minus x squared minus 2. which makes sense, right? I've definitely made my radius bigger. I've added 2 to it. But I do encourage you to think of the radius generally as the distance between your function and your axis. And the way we find distance between things is by subtracting them. My inner radius is going to be the inner function 0 minus -2. Here's my inner radius. So simplifying this, my outer radius is just 100 minus x squared plus 2. So it's 102 minus x squared. And my inner radius is just 2. And then the volume would be the integral from -10 to 10, right? Still the same limit of integration of pi times my big radius squared, or my outer radius squared, minus my inner radius squared. So similar, but not quite the same. Let's look at 2 more iterations of this. So let's say we wanted to instead rotate around y equal to 105. I should point out your axis of rotation shouldn't cross through your region. If it does, then like the region kind of wraps back on itself, and it's not really, it doesn't make sense physically as an object. But sometimes people make mistakes. So if you have a problem where you see that happening, you should probably ask your teacher what's going on. So now our axis of rotation is above our region, right? It's like up here. And of course I did myself a disservice of drawing it this way, because now I want to rotate it up that way, and I left myself no room to do that. So well, I can still do it. I can make it work. So we're going to take this strip and we're going to rotate it up that way. So it's going to look like the following. Let's have some room here. So we're rotating it across this axis of rotation. We're going to get, this is where my drawing skills start to become challenged. So there's our washer now. And here is our inner radius, and here is our outer radius. Okay, so now check this out. The inner radius is the difference between these 2 functions. So it's the difference between y equals 105 and the actual function y equals 100 minus x squared. So our inner radius is 105 minus 100 minus x squared. Our outer radius is the distance between these 2 functions. So it's the top function, 105, minus the bottom function, which is 0. Okay. So again, I want to emphasize, there's not a lot of these problems on the homework, but definitely there's a couple where you have different axes of rotation. So if you have a different axis of rotation, the radius is just the distance between your axis and the function. But you have to think about which function's further away. So I really want to point out, in the previous example, the function 100 minus x squared was the further one. And so the outer radius was 100 minus x squared minus 2. Whereas in this function, the outer radius is the function that's further away, which is y equals 0. So the outer radius is 105 minus 0. So then this ends up being 105. This ends up being 5 plus x squared if we simplify it. And so then our total volume is going to be pi times the integral from -10 to 10 of your outer radius squared minus your inner radius squared. Okay. One more thing for this particular one, and then we'll do something else, maybe, if we have enough time. This clock feels even more off than it used to be. Let's say we want to go around the line x equal to 11. So now this is going to be a little bit wonky. Still got the same good old region here. But now here's our axis of rotation. So unlike the previous problems, where our axis of rotation was a horizontal axis, in this problem, our axis of rotation is a vertical axis, meaning we're going to have to use horizontal strips. So I think about rotating this horizontal strip around the x-axis, I'm going to get this kind of washer. Where this is my inner radius and this is my outer radius. Now, this is a little funky in that my inner radius is going to be 11 minus my function. My outer radius is going to be 11 minus my function. But they're not the same because we have to take our function, which is f of x equal to 100 minus x squared, and we have to write it as a function x is a function of y. So I'm going to write this as y equal to 100 minus x squared, and I'm going to solve for x. So let's see, I've got x squared equal to 100 minus y, and x equal to, now this is where this is really important, plus or minus the square root of 100 minus y. So here's the thing. This inner radius that's r, that's 11 minus the function, it's actually 11 minus the right side of the function. And the right side of the function is where x is positive. So that's going to be 11 minus the positive square root of 100 minus y. Whereas the big radius is 11 minus the left side of the function. And that's going to be 11 minus negative square root of 100 minus y, which is a little weird, but perfectly fine. So then the total volume is going to be pi times the integral of your big radius squared minus your little radius squared. And in this case, it's a dy, because it's a horizontal strip or horizontal slice. So that's going to be pi times the integral of your big radius squared, which is 11 minus, I should really just write 11 plus, because it's 11 minus a minus, so 11 plus the square root of 100 minus y, quantity squared, minus 11 minus the square root of 100 minus y, quantity squared. Now, unlike the previous three problems we did, the limits of integration are not negative 10 to 10, because those were my leftmost xy to my rightmost xy. But now since our strip is horizontal, we're asking how far down can it go to how far up can it go? And the answer is from 0 to 100. 0 to 100. Okay. I do want to point out that this integral, although it looks terrible, is actually not that terrible. So we actually we're gonna do a little bit of simplification just to see how it's fairly doable, and then we'll maybe finish it, maybe not. Probably not, because it's probably still terrible. So if you multiply this out, 11 plus 100 squared 100 minus y squared is going to be 11 squared plus 2 times 11 times the square root of 100 minus y plus the square root of 100 minus y squared. So 100 minus y. Which looks awful, but just wait. Minus, then we're going to do the same thing here. So 11 squared is 121. And then we're going to get 2 times 11 times negative square root of 100 minus y. So we're going to get minus 2 times 11 times the square root of 100 minus y. And then we're going to get this squared, so we're going to get plus 100 minus y. And what I want you to see really here is that almost everything cancels out. 121 minus 121 cancels. And 100 minus y minus 100 minus y cancels. So what you're left with is pi times the integral from 0 to 100 of 2 times 11 times the square root of 100 minus y plus 2 times 11 times the square root of 100 minus y. So it's actually 22 plus 22, so 44 times the square root of 100 minus y, which I would write as 44 pi times the integral from 0 to 100 of 100 minus y to the 1/2 power. And that's not too terrible as far as these problems go. You could integrate that. Okay, 5. The integral of 100 minus y is to the 1/2 is 100 minus y to the 3/2 divided by 3/2 or times 2/3, and then also divided by a -1 because of the negative there, so times a -1, and then from 0 to 100. Or you could do a u sub, but it's not like you have to do a u sub there. Okay, do we have time for one more thing? Let's see. Yeah, I feel like, okay, fine. Yeah, let's do one more. So, stop honking out there. One thing I want to point out is someone could ask a question like this. So let's go back to, let's go back to area for a second. So find the area. Let's do it that way. Under f of x equal to the natural log of x for x between 1 and sure. So let's draw a picture. So natural log of x looks like this. It does cross the x-axis when x is equal to 1. And here's x equal to e squared, which is just a constant, right? E squared, I don't know, it's like 7 point something, but it's just a constant. So we're trying to find this area. And now here's the issue. We can easily set up this integral, right? The integral is not too bad. It's going to be the integral from 1 to e squared of the natural log of x dx. But the problem here is that we don't currently have the ability to find the antiderivative of the natural log of x. The derivative of the natural log of x is 1 over x, but the antiderivative of the natural log of x is something we need integration by parts to be able to do. So if someone asked you to calculate this area, you'd have to switch it up and say, well, instead of using a vertical strip, which this would be, I'm going to use a horizontal strip instead. So using horizontal strips, we're going to do the integral from a low value of y equals 0 to a high value of y equals, we'll figure it out in a minute, of the right function minus the left function. So I need to find a couple things. First, I want to find this upper value here. Well, I know that at that point, x is equal to e squared, and y has to be the natural log of e squared, which is going to be 2. So that's actually a nice upper bound. And looking at my picture, what's my rightmost function here? Well, it's x equal to e squared. Now, what's my leftmost function? Well, it's y equal to the natural log of x, but I don't want to put a natural log of x right there, right? If you see a dy, we can't be putting x's into our integral. So instead of putting y equal to the natural log of x there, what do I actually need to put? Well, I need to solve for x. If y equals the natural log of x, that's the same as x equal to e to the y. So if someone's asking you to integrate natural log of x, what they're really asking you to do is change up your area so that you're integrating e to the y. Because we know how to integrate e to the y. So then this problem becomes pretty straightforward. Be careful though, the antiderivative of e squared isn't e squared. It's e squared times y, because e squared is just a constant, and the integral of a constant is the constant times the variable. The antiderivative of e to the y is e to the y. From 0 to 2, then we plug in, we get e squared times 2 minus e squared minus e squared times 0 minus e to the 0. Be careful. This is an excellent example of a problem where you might accidentally think that when you plug in 0, you just get 0 minus 0 and it goes away. You don't. You end up getting 2e squared minus e squared, which is e squared, minus 0 minus 1. So you actually end up getting e squared plus 1. Don't miss that plus 1 there.